Alrighty, we are going to return to some more familiar territory as we begin Chapter 17 and return to electrophiles and nucleophiles. So you should be really proud of yourself. Look at the litany of nucleophiles you already know. Sodium chloride, maybe potassium hydroxide, methanol, ethanol, amines, nitrile, cyanide, acetylide. You can deprotonate an alkyne and make a great carbon nucleophile. Another great carbon nucleophile is an enolate. Alkenes as nucleophiles, alkynes as nucleophiles. Holy cow, you know a lot of nucleophiles. And guess what? You know a lot of electrophiles too, from the proton to good old-fashioned carbon electrophiles, where either we're talking about a carbocation or just any carbon bearing a leaving group, bromine, peroxy acids. You know a lot of electrophiles and nucleophiles. So why do you need to learn more? Well, because they're darn important. In fact, some of these same nucleophiles are running around in you and making you be alive and functioning. So we will learn about the hydride nucleophile now. We know NaH, but NaH has never reacted as a nucleophile. It's always been a base. Now we're going to learn some other hydride reagents that are nucleophiles. And we're going to learn about some other carbon anion nucleophiles, carbanions, that are super useful. In addition, we're going to learn about a new super important carbon electrophile, that being the carbonyl. No surprise here. We know that resonance contributor from day one practically of OChem, that this is a good resonance contributor. This is a superpolar bond. So that carbon hits a good carbon electrophile. So that'll complement the carbon electrophile we've known all along here, the carbocation or carbon bearing a leaving group. Now, to clear it all up, we will learn in the next several chapters that there are a variety of these different kinds of electrophiles, either aldehydes or ketones, or +3 out. Let's dive in. The good news, new nucleophile, new electrophile, really not a new mechanism. Stuff we've seen. Never a bad idea to review Chapter 7. So what's going on here? Well, we've already pointed out that carbon is a good electrophile. My nucleophile, H- in this case, is thus going to be attracted to that electrophile. When it gets there, it is going to kick that pair of pi electrons out and onto the oxygen to give you this tetrahedral intermediate. Okay, so that's an important intermediate that is formed when your nucleophile attacks the CO double bond. The fate of that intermediate kind of distinguishes the next several chapters. If Y is a terrible leaving group, like say Y is a hydrogen or an alkyl group, we are not going to kick out Y with its pair of electrons. No way, no how. So if Y is a poor leaving group, then that nucleophile, this blue H in this example, is going to stick to the carbonyl carbon, and you have an addition reaction. On the other hand, if Y is either a good leaving group or can be converted to a good leaving group, then it stands to reason that that oxygen could slap its pi electrons back down, kick out Y-, again it has to be a good leaving group, and regenerate this very strong carbon-oxygen double bond. In that case, this is a substitution reaction, where clearly I have substituted my H- here for my Y- here, substituting that out. That's pretty much everything you need to know for the next several chapters. And as you can see, it's just, nucleophiles and electrophiles. All right, so this chapter, all about the addition reactions. Subsequent chapters, we'll be studying the substitution reactions. So you're thinking, blank, I don't have any room in my head to learn any more new reactions. But wait, look, the beauty of OChem. This guy, here, they're all just polar bonds between a carbon and a more electronegative atom. They're all going to undergo the same exact reactivity pattern. So it's not a whole bunch of new reactions, it's just the same old reaction. Even these guys, when you are faced with these particular molecules in a reaction, you're going to say, there's a carbon electrophile, there's a carbon electrophile, carbon electrophile, carbon electrophile, carbon electrophile, carbon electrophile. They all react the same way. So just focus on the functional group. So as soon as I say that, then I say, yeah, but. There is a twist, I will admit it. Conjugated carbonyls are a little bit different. Having said that, though, the good news is we already learned all this stuff. You already know this stuff. So back in the IR chapter, we looked at the ketone CO, that big, honking, strong CO double bond stretch at 1720. But then, what's up with a conjugated CO? The stretch is a little bit lower, around 1700. Why? Because it's conjugated. And there's this resonance contributor that we can draw as such, and it gives us the single bond character, hence the stretching vibration, weaker, a little bit lower wave number. Similarly, when we looked at a conjugated diene, so here's our multi-center MO from butadiene. We learned all this in chapter 14 now, and we found out that when I have a conjugated system, things are different. That because of that multi-center MO, I could have 1,2 or 1,4 addition across the extended pi system. So we just keep reviewing stuff we've already learned. Reactivity of a conjugated CO is going to pull all these concepts back together again, because we can look at that resonance contributor. We now know that there's going to be an electrophilic carbon there and an electrophilic carbon there. So there's two places a nucleophile can attack. And since this is my conjugated pi system, it's just like we saw with the diene. We've got a 1, 2, 3, 4 conjugated system. It's just that now one of the atoms in my conjugated system is an oxygen, not a carbon. But this is an example of my 1,2 electrophile, whereas this would be an example of 1,4 addition. So to illustrate more clearly, I now know that my nucleophile could attack at the red electrophile, 1,4, or the green electrophile, 1,2. If it attacks green, I'll end up with that alcohol. If it attacks 1,4, well, because I end up with an enolate intermediate, that will give me loss of the double bond and regeneration of the carbonyl. And we'll look at that mechanism in great gory detail later. But that's the conjugation twist. Clearly, it's a little problematic because it means we're going to have to think about, what am I going to get, 1,2 addition or 1,4 addition? All right, and then there's the phenomenon of the level of reactivity. They all do react the same, but some of these carbonyl or carboxyl electrophiles are more reactive than others. So for example, aldehydes are a lot more reactive than ketones. Why? Again, super good news. We've already learned everything we need to learn to be able to explain this. Why does HCl add to give me this 2-hexane instead of a 1-hexane? Well, because it's all about the stability of the carbocation intermediate. And because I have 2 alkyl groups pouring in electron density on that carbocation, it's more stable, and I end up making the Markovnikov product. Well, okay, how about this example? Another example of selectivity. My nucleophile here, my acetylide, selectively reacts at the less substituted carbon on my epoxide. Why? Well, it's less crowded. It's sterics. Under these basic conditions, it's governed by how quickly can my acetylide attack. And it can attack the terminal carbon much more quickly than the internal carbon. Up here, the selectivity was due to electronics. And you know what? It's always sterics and electronics in OChem. They explain everything. So, again, comparing aldehydes to ketones, how can we explain why aldehydes are more reactive than ketones? Well, sterically, it makes great sense. That's just a little teeny tiny hydrogen. It doesn't want to, it's not going to block the incoming nucleophile from coming in and making that bond at all. Super fast to attack the aldehyde as compared to the ketone. Furthermore, the ketone is going to be less reactive because it has electron density pumping in to the carbonyl carbon, making it less electrophilic. So sterics and electronics say aldehydes are more reactive. Well, that's it for this big overview. Kind of wrap your head around the whole big picture of the next several chapters. Another piece of good news as we sign out is that we just learned about oxidation states and how we can look at those reagents and say, man, it's pretty obvious that they are going to oxidize something because they're loaded with oxygens. Well, you know, we're learning these new reagents. What are they? They're loaded with hydrogens. And if they're loaded with hydrogens, then it stands to reason that they are reducing agents and they will undergo reactions that are reductions. So, it all fits into neat little patterns, which is also a pattern in these mini lectures to tell bad jokes at the end. So here's the bad joke for today. It's about a policeman who stopped a woman for speeding. He basically pulls her over and asks to see her license. He takes a look at it. He says, "Lady, it says here you're supposed to be wearing glasses." "Well," she says, "I have contacts." Policeman responds, "I don't care who you know. You're getting a ticket anyway." Get it? She's got contacts, you know? Hey, boy. Okay, well, I hope that was worth waiting for, and I hope you enjoy this little send-off, and we will see you in class.